Here's an introductory example with, instead of a discrete random variable, a continuous random variable. And specifically, we're going to focus on the case that's analogous to the one kind of continuous distribution we've used before, which is the normal model. Here's a quantity that instead of having just a few different values, it can take on a whole range, a continuous range of values. But a lot of the ideas are quite similar, and I'll point out the one thing that's really different. So remember our picture of a normal model. It's this bell curve. This is an idealization of a histogram with lots and lots and lots and lots of data and a very small bin width. So you just want to really think of it as the smooth curve that's an approximate idealization of a very nice histogram. And remember the two parameters for a normal model is where's the mean, mu, and what's the standard deviation, sigma. And of course, those are the things we've been talking about lately with discrete random variables, the mean and the standard deviation. The one thing that's different, the key difference, that's not working for me too well. The key difference, even though mean and standard deviation are going to make sense, is that there's no such thing that the probability of this random variable, let's say x, equals some one particular value of x, okay? This doesn't really make sense. If you have to make it make sense, it's going to be 0 all the time, okay? What's the probability? If I measure the length of a piece of wood, what's the probability that it's exactly, say, 5 centimeters to infinite precision? In other words, 5.0000000 all the way to infinity centimeters. It's going to be 0. It's not really going to be that exact, okay? So we can't pin down a continuous random variable to an exact value. But we could look at the probability that the random variable is between 4 centimeters and 6 centimeters. In other words, we can do exactly what we were doing with normal models before. Let me erase this to give a little bit of room. Is look at what's the probability that I'm in some range of the histogram. It's really, really, really similar to what we were doing before. Before we had actual data, and we said what percentage of the data is between two values, like maybe between mu and mu minus sigma, one standard deviation lower than the mean. Now we're just applying those same ideas to probability. Whenever you can have something from a histogram that's like what percentage of an existing population satisfies some property, like is in this range, then exactly the same ideas, exactly the same picture is going to apply for the probability that a bunch of future stuff that's predicted by this model is going to have that property. So I really want to emphasize how similar it is to what we know from the data side. Okay, so one of the things that we used a lot there, which we should remember, is z-scores. So if this is like one standard deviation below the mean, that's, remember, where z equals -1. And the mean, of course, is where z equals 0. So we want to remember that language of z-scores that applies to the normal model. And it just means measure everything in terms of how far are you from the mean and measure in units of the standard deviation. Okay, so let me look at an example from the book. See if there we go. I copied it off this time. The way the camera works, I don't know if it works too well to look at that, but let me read it off and then we'll copy it off. In the 4x100 medley relay event, 4 swimmers swim 100 yards, each using a different stroke. A college team preparing for the conference championship looks at the times their swimmers have posted and creates a model based on the following assumptions. The swimmers' performances are independent. That's going to be really crucial because let me just leave it. The swimmers' performances are independent because all of our assumptions, or almost all of our assumptions about how random variables combine are much, much, much simpler when things are independent. Each swimmer's times follow a normal model. That's not necessarily a very accurate assumption, but it's the only model we have any knowledge of at this point. And the means and standard deviations are given by a table here. Okay, so let me just go ahead and recreate that. Swimmer 1, the mean and the standard deviation are 50.72 seconds and 0.24 seconds. Swimmer 2, 55.51, 0.22. Swimmer 3, 49.43, 0.25. And swimmer 4, 44.91, 0.21. Okay. Notice how small those standard deviations are, but that is realistic, that you get to this time and it's really hard to get much better than your average time by more than a quarter of a second. Okay. So here's a basic question we could ask. This is an intro. It's not really asked in this problem. I'm not changing colors just because I like it, just because I'm trying to baby these pens along and I need to get new pens. What's the probability, let's say, that on the next swim, and let's call this x1, x2, x3, and x4, that swimmer's time 1 will be less than 50 even. Okay? So their average is 50.72, not a big standard deviation. That would be quite an accomplishment for them. How would we get that? Just want to remind you, that's really something we already know how to do. Even though it's couched in the language of probability and all that kind of thing, it's still the good old normal model. We can just think of it as the usual problem, where we've got something described by a normal model. The mu here is 50.72, and the sigma is 0.24, and we're out in this little tail here. Probably pretty small. Okay, so we could do that on the calculator. Let's heat the calculator up here. Go to, see if it can focus, normal CDF, our friend. Now lower it says minus 1e9999. It's suggesting let's have an absurdly, hugely negative lower limit. That's great. That's fine by me, because we don't have a lower bound. We don't want to have any lower bound for the time here. We just want an upper bound of 50. The mean is 50.72, and the sigma is 0.24. Okay. Now I just go to paste. I'm using the wizard. Not everybody has this, but all it does is it just reminds you basically of how to enter this in. All it does is it creates the function normal CDF, lower, upper, mean, standard deviation. Okay, 0.00135. So about 0.135%. Very low probability. It would be stunning. One chance in almost 1,000 that they would beat that time of 50. So they probably shouldn't expect to do that. Okay. Now, so what that points out is that kind of question is really too simple for us to be asking right now. That's not challenging enough. It is important for us to remember, for us to link this to the old stuff with random variables, for the old stuff with distributions, basically, and statistics. And we're saying that the same ideas apply when we're thinking in probability terms. Here's a more interesting question, okay? Let's look at this is a relay. So what we're interested in is the total time. So a very reasonable question to ask is, what's the expected value of the total time for the relay? Great thing about expected value is that that's always the sum, no matter what, even if they're not, I guess I can write that in, even if they're not independent. We are assuming that, but even if they weren't independent, then the expected value of a sum is the sum of the expected values. Okay, so that's easy. Okay, so that's just going to be, let's do that on the calculator. We got 50.72 plus 55.51 plus 49.43 plus 44.91. No, you can't see that. Okay, here we go. 200.57. I haven't used these markers in a while, and I forgot they were getting so bad. Okay, so that's the expected total time. It's just the total of the mu's. That's great. Okay, what about the total standard deviation? What's the standard deviation of the total time? Okay. Now remember, what is additive there is variances, and the standard deviations therefore satisfy the Pythagoras law. And that is really assuming independence. This is where we're assuming that these aren't correlated to each other. So, and that might not be true. Maybe if one person swims badly, maybe that's for a reason that affects everybody else. Maybe it's because the water's too cold or too warm, or it's a weird stadium, or the lighting's wrong, or people yelled at the team members beforehand. So it's maybe not a great assumption, but let's try and make it. Let's try red. I haven't tried red yet. Okay. So the standard deviation of the sum is going to be the square root of the sum of the squares. All right, so that's going to be the square root of, well, let me just do it out on the calculator. So we're going to do square root of 0.24 squared plus 0.22 squared plus 0.25 squared plus 0.21 squared. Alrighty. 0.46. So it's 0.46. Notice that's substantially less than the sum of all these guys. And that's what happens when you sum independent standard deviations, is that they're going to be less than the sum of these by a factor of about root n, where n is the number of things you summed up. So if you added these up, it'd be almost a full second, and we get about root 4 or 1/2 that much standard deviation. Okay, so here's the real punchline of this, the normal model thing, okay? The sum of normal models, if I take a sum of variables, independent variables described each by a normal model, this is one of the big reasons people use a normal model. Not necessarily because it's incredibly accurate. It's that the sum is itself normal. All that normal CDF stuff, the magic button on the calculator that gives us the area under that special shape, it's still going to apply when we combine things with a sum if they're independent and if they're individually normal. That's a big deal. If the individual ones have complicated distributions, the sum can be very, even more complicated. This is a wonderful thing. So it allows us to answer questions like this. Let's see. 0.46. Let me actually put over here the sum. We've now got a new normal model for the sum, 0.46, and the mu, I still have it on the calculator, thank goodness, 200.57. Okay. So that allows us to answer questions like this. What's the probability that the sum is under, let's say we want to get the magic mark of 200 seconds. We expect that might be the winning time. That's our goal. What's the probability that's going to happen? Okay. That's, again, going to be a normal CDF. And it's going to be, whatever huge negative number you want. This could be like 0. It doesn't have to be this ridiculous negative number. Okay. But we're going to put in this mean and the new standard deviation. So notice how that information had to come in first to say, okay, is 200 good or not? I mean, is that a really good score? Well, it's a bit under. It's a roughly 1 z, it's like z equals -1 roughly. And we could calculate the z-score if we wanted, or we could just let the fancy version of normal CDF do the work. Okay. And so now this is going to be 200. The new mean is 200.57. Let me stop moving it around so you can see it better. 0.46. Paste that in. Looks good. 0.08, 10.8%, let's say. Okay. So that's going to be, I'm glad this red is working better than the other markers. 10.8%. So that's not unrealistic. It's not incredibly likely. I wouldn't bet on it at even odds. But maybe about 10% of the time, given all these other assumptions, we might expect to crack the 200 barrier. So the ideas here were that first, that the normal model on its own terms, don't be scared by the whole probability language. We actually have done almost exactly this stuff before. And now we're talking about this really nice thing that when we add up random variables, we know what means do, always simple. We know what sigmas do, Pythagoras, if independent. And we know how the probabilities work if they're normal and independent, because then you just figure out the mu and sigma by the laws I just alluded to, and we use this huge fact that the combination is still normal. Note, I have not proved to you this fact that the sum if I have a sum of random variables, that it's still a normal distribution. That's a big theorem, which we're not going to prove the details of, but it's going to be terribly, terribly useful to us.